Good morning. Yeah. Okay. Good morning. I was asked to talk a little bit about the global distributions of aerosols. So I give you some numbers. So you see a lot of plots now with numbers. We talk about global aerosols of the tropospheric aerosol, volcanic aerosols. We talked earlier to these massive events with last couple of years that are not included here. So it's just tropospheric aerosol, but aerosol is highly diverse. And I will talk about global aerosol and also give you a number of what are the climate implications. Oops. This one? Oh yeah. So first the overview. First I talk about atmospheric aerosols in general. So you got already introduction. Then I talk about aerosol optical properties and observations. So normally when you make climate assessments, you use global models. I try to do a different approach by going directly from observations. So then I talk about these global distributions with the climatology I developed from observations. From this, I was able to deduct from absorption and optical depth measurements of different size aerosol how much components contribute. And I give you also global distribution of these components that are kind of in agreement with the global modeling. Then I talk about aerosol radiative effects. So what is the impact on the surface radiation budget, on the atmospheric heating, and also climate-wise at what happens at the top of the atmosphere. And then I talk also in the end about indirect effects. They're really a big issue right now. And if we want to reduce climate uncertainty due to aerosols, we have to get a better control about the indirect effects. Indirect effect means how aerosol modify clouds, and clouds also are the major player in the radiation budget. So I have a nice introduction paper on aerosols. So you see some nice different compositions of aerosol, dust storms, volcanic, wildfires. We have sea salt aerosol, we have soot, that's very absorbing aerosol. So you get a variety. What you should remember is at the bottom you see this, there are different sources and they have a lifetime of only a few days. So there's a lot of variability. It's never the same. It changes from day to day. And so it's not like you make gas measurements and they're valid for the whole globe or over the whole year or seasons. Here you have to make measurements again and again and again at a high frequency in order to capture the statistics. So aerosol optical properties are really essential in my work, and also when you want to get the climate impacts. You want to know how much is there, and that's where we use normally sun photometry from the surface. We do it also from satellite, but from satellite we make a lot of assumptions, so we're better off and higher accurate if we do it from the ground. We do it via visible intonation, or let's say what you showed earlier today, where you look at like how much energy is lost in the atmosphere with the paintings, then how absorbing it is. That's very important, especially for the climate impact. And we try to quantify it through the absorption aerosol optical depths. We have a term we call single scattering albedo, SSA. That's a measure of how much of the lost energy is scattered, and the remaining part is not scattered, that's absorbed. And so we have an absolute value. And so and then you need the size. The size is also, we want to know if it's a large size or a smaller size. Smaller size is more from wildfires and from pollution. Larger size we normally get from sea salt and from dust. And also these sizes are very elementary in terms of the color we see in the sky. So if you have a lot of dust, it takes the color out of the sky. And maybe I could have shown you nice pictures. I did a lot of ship cruises. You see the ship here. And so we made a lot of pictures there. And also on the ship, we had some of these photometers, and we tried to supplement these data into a database that is operated by the NASA at Goddard, the Maritime Aerosol Network. And it's a really big effort in order to get better aerosol data over oceans, which cover 70% of the globe. And the aspects, and we also have model interpretations, but again, that's I try to stay away from this at this point. global distributions. On the upper right side, yeah. No, on the upper right, you see these maps, and on the left side, you see, here. These are the small sizes, that are the big sizes, and that's the absorption of the small sizes and absorption of the big sizes. And you see the scale is going, it's stronger here. You see these peaks over Asia, where you have more fine mood from pollution. You have for the coarse mood more dust over the Sahara. And that's the absorption. The absorption we cannot get directly with sun photometry because you need inversions. And so we have no data over oceans. In order to get complete picture, so what I did is then I used patterns from global modeling, adjust the patterns, the regional patterns, and expand these data. And then I come up with these global consistent fields. And here you see the fine mode AOD, the small particles. We have biomass burning here, pollution over here, we have dust over here, and then the associated absorption. So where you have more optical depths, you also have generally more absorption. You see the same scale, it's basically because I have to multiply it by 10 in order to make it similar, but you get an impression how it's distributed. And from this one, I'm able, from these 4 measurements, on the right side here, I can extract how much black carbon, organic matter we have, sulfate, sea salt, and dust, because we have 5 input parameters, and from this I can do then show on the next one. And that's, I make assumptions about these components in terms of size distribution and refractive indices. So we are just looking at mid-visible data at this point here, at this wavelengths. And by defining these components, you automatically get data over the whole spectral range. And that's very helpful later on when we make radiative transfer calculation. And now you have to look at all these distributions here. Now we have a total optical depth of 0.12. That is this field. See, if you look at this value and you look at this variability, there's a lot of variability in there. So it's evenly distributed. And there's even seasonal variations with it. And then I split it up into the big particles and the small particles. So here you have the big particles with a lot of sea salt up here, and here a lot of dust. Over here you have the fine mode, mainly over land from wildfires and from pollution. And then you can split up this coarse mode again into dust and in sea salt. Here on the right side, you see the global annual averages, these are annual maps. And on the right side, you see the fine mode is separated into sulfate, organic, and black carbon that's multiplied by 10. So it's actually 10 times smaller, but otherwise you wouldn't see anything on the color scale. Also here on the bottom, I show you the anthropogenic AOD. From modeling, we get an idea how much of the total fine mode is anthropogenic. And you can see the anthropogenic since 1850. That is this one. Oops. So this one is only about a third of the total AOD. But again, these are all small particles, so they bring up a lot of particle numbers. And with a lot of particle numbers, you have impacts also on clouds. On the right side, you see my estimates for anthropogenic component. Also on the right side here. Oops. Got it here. There. And this is anthropogenic sulfate, anthropogenic organics, anthropogenic black carbon, and I have another solution what anthropogenic black carbon could be if there was more black carbon now since pre-industrial times. I also give you an estimate for anthropogenic dust, also multiplied by 10. It's a relatively small value. It's probably only a third of the anthropogenic sulfate, but due to land changes, we also expect change in anthropogenic dust. Then, since I have made these properties for these components for all different wavelengths, you can make then when you get the AOD, for instance, automatically, if you have if you know this field, you automatically define this field at 450 nanometer in the UV, at 1 micrometer in near infrared, and here at 10 micrometer in the far infrared. So you automatically have defined these fields. And then, of course, it's very easy. You plug it into a model, and then you come up with these radiative transfer calculations. So this is my climatology. I make a small advertisement. So if you're interested in global fields of aerosols that are typically what to expect, here you can download those. And later on we can, next one. Now I come to the application. So I try to apply this climatology, which I have for different years, into a radiative transfer scheme. And what you do in a radiative transfer scheme is, So you have our current aerosol condition, then you put it in a radiative transfer scheme with clouds and surface, albedo, and temperature, and then you make the radiative transfer for solar infrared, and you do the same once with aerosol and once without aerosol, and by difference you get the total aerosol impact, and that's what I'm showing you. In a second, I show you what is anthropogenic, where I take what we have aerosol today, I make an estimate, what's kind of difficult, how much aerosol we had in 1850, and do the same thing, and also by difference, I get the aerosol impact. And the things I'm interested in are what are the radiative flux changes at the top of the atmosphere, that's the impact of climate. In the atmosphere, what's the impact on dynamics? And finally, on the surface, what's the impact on surface processes? So if I put all my aerosol with kind of a climatology from 2000 to, for the Aeronet age, from 1995 to about 2020, and then I plug it in there, that's all aerosol, not anthropogenic. Then that's the impact of what you get. And you have a cooling is, you can't see it here in the bottom, it's too bad. So if it's yellow down here, it's a cooling, and if it's going over here into the red, it's a warming. So you see on the top of that, and climate impact is overall a cooling, but over the Sahara, because it's very bright surface and there are IR effects, you actually get a warming. And for the atmosphere, you get in regions where you have absorption by dust and by wildfires, you get strong warming, a lot of heating. And at the surface, of course, it's attenuated, so you measure the losses, and that's what you get at the surface. Now, if you split it up into contributions from the solar radiative transfer, like the interaction with the sun, and also the thermal effect, there's also a thermal effect, especially if you have elevated dust. And so here you have the solar effect. Now, unfortunately, you don't see it here. Here's a red spot, and that makes it red. So there's an infrared effect, especially that's almost as big as the solar effect where we have dust. So you should not leave out thermal IR if we have dust. Then we have the surface again. You see there's a solar effect and there's an opposing thermal effect. So the solar effect is actually larger than the total effect at the surface. And finally, I thought I would just show you this one because it's reflecting what a satellite would see. Like if you have a series satellite and measures the broadband fluxes, that's where you would see hotspots. So you would probably see more in the dust outflow region of the dark oceans here and then over land because it's high reflecting. That's if you have a surface measurement at the ground, you make a solar flux radiation on the surface. That's where you would see the largest signals from ground observations. So you kind of get an idea where you put your instruments in order to make good measurements that could lead, can be combined with these global data. Now the total, we have also seasonal effects. You can go quickly through this one. You see there's also seasonality for the total effect. And you see where the dust You see also in May, April, June, and June, July, August, we have here a really strong dust warming over the Sahara. And then, of course, you can do it again, split up into atmosphere. It's a warming over here. And here we at the surface, we have the surface cooling. Now we can go through the components. Remember, we had the total, and now we try to split it up. How do different components contribute? And my components were dust here, sea salt. So here we have the fine wood. Here is sulfate, organic carbon, black carbon, and if you combine black carbon, organic carbon. Again, this is a forcing, the radiative forcing, and global annual averages, and here's a global distribution. And again, what you see is that's not a single value. You have really a lot of structure, a lot of global distribution, also seasonality. Here you have the AOD maps, and here's the associated forcing. And you see, generally, it's all more yellow, so it's more cooling. Warming, where you have these red ones, you only see for black carbon. But when you take black carbon together with organics and sulfate, it ends up it's always end up with a cooling. So if people pick out black carbon to say, if you mitigate black carbon, you also mitigate organics. So the impact will not be as large as you might think, because they're co-emitted. Next one. Oops. Yeah, trends. I tried to use MODIS data from the last 20 years. So we had from 2000 to 2022 MODIS data. And so we determined, I took here 7-year periods, and compared it to 7-year periods and compared it to other ones before. So here we have 6 years over here against the 6 years in the early 2000s, and then it's the next section. But let's focus on the lower one. This is the one where we have from the most recent 6 years to the years early 2000. And you can see the forcing has not changed very much at the top of the atmosphere. But in here, we see a lot of, for the atmospheric, you see a lot more warming over here, over pollution over India. And you see also a lot more less warming because we have less aerosol over China. So there are some regional changes. And this will also see at the surface similar. Of course, you have more losses at the surface because you have more aerosol over India, and you have less over China. But you also see it in terms of global averages. That's here a minimum, and then here, since the last years, it's decreasing again. So we have the maximum around 2010, and then the global aerosol is reducing again. Also in terms of radiative forcing. So that's my summary on these. It was a lot of numbers and a lot of pictures to look at. So I tried to condense it into a small summary here. So first, aerosol radiative effects, they are small compared to clouds. They are only interested to climate modeler because clouds are part of the system and aerosol is added to it. So it's an anthropogenic source. Overall, the aerosol has climate cooling. Globally, for the total aerosol we have now, it's not the anthropogenic effect. Globally, the aerosol without volcanic eruptions, where sometimes really pop it up a little bit more. There are several watts, but only for a couple of years. But troposphere aerosol globally has a cooling of 1.2 watt per meter square, and you see the contributions from the different components on the right side. We had a maximum of the radiative effects about 2010, and since then it's slowly decreasing, but it's slowly, it's not a big thing. We have very uneven distributions. We have hotspots, as you could see over China and India, where the hotspots kind of offset each other. The cooling is normally strong over dark surfaces, over deep oceans. We have significant topos atmosphere, thermal air warming near dust source regions. The solar atmospheric heating by absorbing wildfire and pollution aerosol is significant. Now, just in the end, a short note to the radiative forcing. Radiative forcing, this is a term we use in order to say how much has aerosol changed since pre-industrial times. And of course, it requires that we know the pre-industrial situation. We have no measurements really. Maybe some of these pictures we saw earlier today, maybe they can help us. I'm not sure if we can do, but it's like one big question, for instance, is, was aerosol at pre-industrial time more absorbing or not? Did we have more wildfires or didn't we have more wildfires? That's really an important aspect in that. So I did this again. Here you see the forcing I calculate here. Pre-industrial, you see the total forcing is about here. That's the total cooling I get. And dust compared a little bit to cooling, sulfate very strong, organics a little bit, black carbon is a strong warmer. And if I do a different scenario where I allow for more black carbon, the warming can be even stronger. So there's significant warming by BC, but overall it's a cooling of minus 0.27. So there's still a lot of cooling there. So that's a direct presence effect from putting aerosol in there. And then the other thing is what happens with the indirect effect via cloud forcing. And that's it's a big issue. We have been working a lot in the science community to quantify it, and it's difficult. We know of definitely that if we have more fine mode aerosol, more number particles, we get more condensation nuclei, and then we get smaller droplets. So the droplets decrease. If the droplets get smaller, albedo increases, and we get a cooling from water clouds. But if you have smaller droplets, then you also get faster evaporation. The particles are smaller, you get they disappear faster, so you have less cloud cover. On the other hand, you have delayed precipitation because then you have more cloud cover. So these are opposing effects. So I present you now my calculation where I assume that the first indirect effect exists, I use satellite observation, and that the secondary effects from this kind of offset each other. Where we have low cloud cover, then the evaporation dominates, and we have a lot of cloud cover, lifetime dominates. That's what I show you here. So on the bottom you see the total cooling. It's 0.94 watt per meter square. So this was a direct effect what we saw earlier, and with the indirect we get this one. So the first indirect effect is this one. The first indirect effect is basically the reduced radius. I use the MODIS satellite-based relationship between CD and C, as a cloud droplet number, and fine mode AOD, what's for aerosol number, and we get this fit here. And I use this fit in order to determine to associate increases in AOD fine mode with the CD and C. And that's what I get. So you get a lot of cooling over oceans where it's relatively dark. And then I make the assumption, that's the first indirect effect, the first one. And then I make the assumption what I told you, where I kind of use the second indirect effect, where it gets warmer over here and colder over here, and then I get a total over here. And this one I combined with the direct, and that gets my total. Now the middle one is only where I didn't account for anthropogenic dust. Here I include for anthropogenic dust. So the point is, the point I want to make is this one is a direct effect from just the aerosol presence of aerosol. And if we include the indirect effect, I can come up an estimate that's 0.94. If it's not distributed the way I have it, I'm not quite sure. I'm still working on it. So I think the last one, the summary. For the forcing, for the anthropogenic effects, again, we are small compared now even to aerosol radiative effects. It's even a step smaller than for the total aerosol. It's only a fourth of the total. It's only 0.27. Again, you get the contribution of the different components. We had the maximum around 2010. and it's now slowly declining. Even though there are a lot of variations, you could see over India there was a strong increase, and there's a forcing getting more negative. Over China, it's actually reducing, and so they actually get, in a relative sense, a warming. Again, there are even uneven global distribution, direct uncertainty. For pre-industrial definition, it's a really big issue. If you don't get it right, that's why we don't know very much about this. The uncertainty is relatively large. I was asked to put something at what we should do with measurements. If it would be me from the climate potential, these are the properties I would like to see have measured. So that's the fine mode AOD, the mid-visible AOD associated with sub-micrometer sizes, the coarse mode AOD, and when we have these measurements over the oceans with the sun photometers, they can split through the spectral dependence between what's coarse mode and fine mode associated AOD. So that's a big help. Then, of course, we really need the AOD, the absorption AOD, AAOD, like how absorbing are these modes. There are ways to do it. They're tricky a little bit, but again, we need information about absorption in order to get to the component. So what I like you to do is become a member of Aeronet and have your instrument and become part of the system. And so, because you also benefit from it, because they provide you with inversions, and inversions give you data on absorption. So you're not alone by yourself. You are in a system that's getting products. What's really important for me is the link to satellite data. And to modeling answers. So if you make local measurements, make sure that you link to satellite data and link to modeling, because then the community gains from it. And so if you pick a site, make sure that the site is regionally represented. Don't go on a mountain. For global modeling, for satellite remote sensing, it's a mismatch, and it makes it difficult. So pick a site that is useful for modeling also on larger scales. It's always good to look at satellite overpasses. Like, you can learn a lot by having a measurement via ALOS, where you make underneath the satellite, where a satellite doesn't have the option to see everything, but on the side, so you can learn a lot by making underpass measurements. And then connect with the satellite community. And of course, I'm involved with Aerocom. That's a modeling and satellite community. They have annual meetings. So if you have time and want to connect to modeling or satellite community, that's the place to go. Thanks.
Thank you very much, Stefan. Vasily.
Stefan, thank you very much for this very nice presentation, for the results and the interpretation in terms of radiation, how the aerosol affects radiation. Yeah. 2 questions regarding the needs that you presented here. You need fine mode AODs and coarse mode AODs. We have recent findings for the coarse mode that Aeronet actually needs to expand in IR. There is a super coarse mode that we don't calculate, right? We have IR measurements, we have people from IR here in order to interpret more in terms of IR absorption or what is really happening in terms of heating of the atmosphere. The second, how you do the typing, right? What are the uncertainties in the typing that you perform? Is it from the model in order to distinguish between natural and anthropogenic aerosols, right? And the third, to conclude with all that and connect it, how new techniques like the active remote sensing would help to bring more information in your climatology, and if you see that in the framework of the Aerosol. Earthcare, Calypso, CATS, we have the EOS from NASA coming, all these missions. How will help your work and your climatology?
Yeah, I think the active remote sensing is a really important part, and we have this Earthcare coming up, hopefully a new satellite. Especially when you talk about the uncertain aerosol cloud effects, it's important that you have the right co-location. Otherwise, you cannot say very much about how they interact. Right now, my estimates for the indirect effect are basically on assumptions how it's distributed. So we get much better statistics. So I think you shouldn't, if you think in terms of aerosol and clouds, vertical distribution is really important. For just the aerosol presence effect, okay, for the dust, it's really important to get the altitude correct. And there it really matters. Even simple instruments like the ceilometer, what we had on the ship, it's a really big indicator where the dust is. So that, but again, it's only a measurement. The problem is we need to connect what we measure locally, globally. So we have to link to satellite data. So again, I see the value of satellite observation that give you global coverage, even though like Calypso is only a track. So it's, you need many years, but we are in a fortunate situation with Calypso that we have now 14 years or 15 years of Calypso data. That gives you some statistics. So we kind of feel comfortable of what we see. Even though there's also interpretation there. And I think Calypso has become better over the years. So if you have a new satellite product, it doesn't mean that it's immediately ready. It takes 10 years sometimes to mature, to learn about the pitfalls. And by now, I think we have a pretty good Calypso data set. So in some way, we have to start to make the measurements. So with EarthCare, I'm a little bit shocked that we have only a lifetime from 3 years or so. For higher resolution, they put, okay, they have a lower orbit. And so we cannot expect a lifetime of what we will see. But again, it is collocated radar and LiDAR. And that makes it's a really strong thing to make studies, at least process studies that we can use in modeling later on. But again, you need to connect what we measure always to some global observations from satellites, and especially to modeling what comes to process study. You asked about the uncertainty, also about what? The aerosol typing was done by, I picked some types basically. My sulfate is basically just fine mode, non-absorbing. And then I have organic that has a spectral feature because we have this brown carbon, we call it brown. Also, anyway, that's more absorbing the UV, so you need this type of component. And then I have black carbon component. But my black carbon component, I always cover already with organics because the lifetime of pure black carbon is not lasting very long. It's very quickly coated. And so I have this type. And then these are my three modes for the fine mode. And then for the coarse mode, I have just sea salt and dust. And the idea is, of course, when you have dust in your model, then you also have to consider different sizes. So if you have information about the absorption, then you get actually information about dust size and the assumption that if you have more coarse mode AOD, your dust sizes are larger. And so actually in the climatology, I actually got information on dust size from the absorption of coarse mode. And for the fine mode, it basically I distributed on the black carbon, and I had to use some help like organic sulfate ratio from global modeling to give me some step in. So there are some tricks with it, but in the end I compared it to data from these component models from Aerocom, where you go from the emissions, you process the emissions, like chemical process and transport process, and then you come up with components. And their distributions and their values are very comparable. And so that kind of gives me, and I feel like they have a lot of uncertainties on their way, and I try to come from observation on a different approach. I call it their bottom up, and I come from the top down, and then we meet and look at the components. But it's very promising that we get very reasonable numbers. On the other hand, when I make the radiative forcing, in the end, I get numbers that are pretty certain because I don't have to deal with cloud variability. If you have a climate model and you make 10 years, 100-year runs, and then this aerosol and then without aerosol, then the clouds change. And you need a lot of statistics in order to filter out the aerosol. Here I can actually filter it by very simple dual calls. So, but I don't have the feedbacks included. On the other hand, there are arguments, of course, that the feedbacks might matter, the quick feedbacks, and but I say, and I think it studies that maybe only 10%, is relatively small. So there's error involved in these forcing calculations I make, but they are done in a very simplistic way. but because they don't include feedbacks. But again, you don't have to deal with the complexity of models you don't understand.
Almost 90% observations, let's say.
Yeah, so for the aerosol, but then from the aerosol to the radiative forcing, I make two simulations, one with and without, and I don't allow for feedbacks.
Okay, thank you, Stefan.
Thank you. Yes, Professor.
Stefan, thanks for such a nice review. Most of your data, of course, have been presented as climatological information in the brightening period. I mean, you know, the solar dimming and brightening. There are two periods that have been discussed in climatology for some time now. Yeah. So these data, I mean, the negative, the minus 2 point something, how it compares to the period after World War II to 1980, which was the dimming period. Because this is the brightening, the solar, I don't know, that's what they say.
I make simulations. Basically, in order to do the simulations, I used relatively changes predicted by climate models. So I scaled it back, and then I got more cooling, of course, but it was not that high. I mean, I think since 1980, the cooling has remained constant, and even though the aerosol increased because of less sulfate, yeah, it stayed pretty stable. And so right now, the aerosol, since 1980, the climate effect of aerosol, the direct effect, has not changed very much. On the other hand, we have less sulfate now, and sulfate is a good nuclei for clouds. So I would assume, since indirect effects cool, that actually the cooling should have slowly gone down since 1980 because of the indirect effect. But that's
and excuse me, you can see that in the different trend in China, because
no, in China we see from the satellite data a clear maximum in 2010, and then it reduced again. That's why I took MODIS data in order to demonstrate. On the other hand, for India, the predictions for models for the future predicted at about 2025 a maximum for India, and it's pretty much what we probably expect to see. So it's still increasing, it still hasn't reached the maximum yet. But again, these are predictions with emission scenarios. It's much nicer to work with real observations. So it's nice to see that in China, actually, we have such a strong reduction since 2010. So it's really going down, and we see also reduced cooling. Also.
So the difference between the 50-year period from 40 to 80 or 40 year and the last part would be what? How much you estimate it would be from dimming to brightening?
I think
climatology of the.
No, I think in terms of aerosol and dimming and brightening, it doesn't matter too much. It's not such a big. It's not a big number. When we took of course, you have globally always uneven distribution. In some regions, you have stronger impacts but I talk about global cooling. So the global cooling was ramping up since 1850 continuously, and then maximum out at that after Second World War around 1820, about 1980, and since then it has been pretty solid for the direct effects. But again, we need to know more about the interaction between aerosol and clouds in order to make a real assessment on terms of climate impacts. But dimming and brightening only refers to the clear sky, what happens under clear sky.
Yeah.
And then there's always on the regions where we have a lot of industrial output, because there are most instruments like in Europe and America. And so it's biased this way.
Also, I was surprised by the values over the seas, the oceans.
They're high?
They were, yeah, maybe I don't see the colors so well.
But
they were quite neutral and not colored.
Oh, you mean there was? Well,
spectrometry. Join the action, join the newsletter. Follow us on social media for news and announcement.